Hey there everybody, Mr. Dickin here. In this video we are going to be talking about how to solve systems of linear and quadratic equations. For those of you who don't remember, a system of equations is grouped together by a squiggly brace, and that's typically where we have two or more equations written out, and we're trying to figure out points at which these equations intersect. Now, when we did this previously, it was just straight lines, so x's and y's, and we use substitution or elimination. A lot of you tended to lean towards the elimination method. Today we're going to be doing it with both linear systems, so typically that's going to be in the format of y equals mx plus b, and then quadratic, and that's going to be ax squared plus bx plus c. So we're going to see some x squareds showing up to the party here. The method of choice for solving these will almost always, not all the time, but almost always be substitution. All right, so let's get a few scenarios out of the way. If we have a linear, so straight line, and quadratic system, there's three different outcomes. Outcome one is maybe our line hits the quadratic in two separate spots. There's two intersection points, meaning two solutions. That's probably the most common. Maybe our line hits the quadratic once and only once. Here in the image, it's shown at the vertex. It's not guaranteed to happen at the vertex. This is what's called a tangential line. So this line is tangent to the parabola. And then it's also positive that maybe our lines just never hit each other. Our line and our parabola never hit each other. With straight lines, we saw this pretty frequently with parallel lines. You can't really call a parabola and a linear function necessarily parallel, but you can say that they would never intersect. So that is certainly possible. Now, if we have two parabolas that we're dealing with, we're still going to have the same concept where maybe they intersect at two separate spots, maybe they share a tangential point, maybe they never intersect each other at all. So one would open up, one would open down, and one's clearly above the other. Or maybe we have a parabola that's directly on top of itself, in which case that would be infinitely many solutions. When we're solving equations algebraically, you'll have no solution if you ever reach a point where it's like maybe 0 equals 7, where all the variables have canceled out and you're left with a mathematical statement that's just simply not true. If it's infinitely many, that means you'd be left with a scenario where you have some constant value equals some constant value. All the variables are gone, you're just left with a true statement. All right, so let's get going. We've got a handful of examples. Most of these we're going to try to do by factoring first. If we can't do factoring, we'll rely then on quadratic formula or completing the square. All right, so number one. And by the way, folks, if you guys need to pause the video at any point to write this stuff down, please, please, please do that. So number one, I'm seeing these are both set equal to y. So y equals y equals. So what I'm going to do is I'm going to plug in this first equation in for that y. Essentially, I'm setting these things equal to each other. Or if you wanted, you could plug this x plus 6 into that way. It doesn't matter. All right, you're just setting these things equal to each other. So we've got x plus 6 equals negative x squared plus 5x plus 6. Sorry for the horrendous handwriting. All right, now since we have an x squared, our goal is to set this thing equal to 0. So ultimately, I want to have a 0 on one side. It doesn't matter left side, right side. We just want it equal to 0. I'm noticing my x squared is currently negative, so I'd like to have a positive x squared, so I'm going to throw that over to this side, which means I'm going to move everything from the right over to the left. So I need to add x squared. There's no x squared for it to add with, so it's just going to be 1x squared over here. I need to subtract 5x. Subtract 5x, so that would be a negative 4x. I need to subtract 6. Subtract 6. Well, that's just a 0, so it's gone. I don't need to write it. All right, so now I've got x squared minus 4x equals 0. As promised, we're going to factor this out. I'm noticing a GCF of x, so we'd have x minus 4 in parentheses. And this gives me my two solutions. I've got x equals 0 and x equals 4. Now these solutions, remember, should represent points of intersection, and points of intersection should be written as coordinates. So I've got 0, comma something, and then 4, comma something. I can plug in 0 for either one of these two functions. I can plug it in for x right here, so 0 squared plus 5 times 0 plus 6, or just 0 plus 6. I'm going to argue this second function is probably a lot easier. So if I plug in 0 for x, we're just going to get 6. Same thing with the 4. I could plug it into either. I think the second one's easier. If I plug in if I plug in 4, 4 plus 6 would give me 10. So these are going to be my 2 points of intersection. All right, let's do one more. X squared plus 6x plus 9 equals x plus 3. Again, I'm going to start this off by setting them equal to each other because they're both equal to y. So x squared plus 6x plus 9 equals x plus 3. If you had this flip-flopped, meaning the opposite equation or expression on the opposite side of the equal sign, it doesn't matter. It still says the same thing. My goal is I want this equal to 0. So that means this x has to go. So we'll have x squared, a 5x. This 3's got to go, and that'd be a 6. X squared plus 5x plus 6 equals 0. So we have an x squared, which means we want this equal to 0. So now we can hopefully factor and solve. All right, so if we factor this, numbers that multiply to be 6 but add up to 5, I'm getting 2 and 3. So my solutions here are -2 and -3. Now that I know my x value, I can figure out my y value fairly quickly. I would argue the second equation is going to be a lot easier to use. So I'm going to plug in -2 for x and -3 for x to get my results. So -2 plus 3 is 1. -3 plus 3 is 0. Hey-o. These are the 2 intersection points for that straight line and that parabola. All right, now let's see what happens if maybe we have 2 quadratics. So this is going to be 2 separate parabolas graphed at the same time. Well, they're both set equal to y, so we can start off by setting them equal to each other. X squared plus 7x plus 12 equals -x squared minus x plus 12 for that first one. For the second one, we'd have x squared plus 2x plus 1 equals x squared plus 5x plus 1. I'm running out of room here. All right. Let's take a look at the first one. All right, it's not equal to 0. I don't like that. We want it equal to 0. So to do that, I'll take everything from the right-hand side and move it over. So if I add x squared, that's going to be 2x squared. If I add x, that's going to be 8x. And if I subtract 12, well, 12 is just gone. Cool. So 2x squared plus 8x equals 0. Now we'll factor. Always look for GCF first. I'm noticing there's a GCF of 2x, and that would leave me with an x plus 4 in parentheses after I factor that out. So my solutions here are x equals 0 and x equals -4. Now we have a little bit more work to do when we're finding our solutions because we don't have just a straight up linear equation to plug these into. Instead, we have to plug them into a quadratic. So there's going to be a little bit more mathing that has to take place. Fortunately, plugging in 0 is super easy. If I plug in 0 for x, first and second terms cancel out. So I'm just left with the c value, aka the y-intercept. So 0, 12 is going to be one of our points. And then if I plugged in 4, let's see, 4 squared is 16. 7 times 4 is 28. And then 12. So 16 plus 28. Oh, this is a -4. I goofed. There we go. 16 minus 28. That's going to be different. Plus 12. So 16 minus 28 plus 12. 16 minus 28 is going to be -12 plus 12. Well, all right, we're at 0. Hey. Another way to do that, if you're not a huge fan of doing addition, subtraction, addition, is you could do the 16 plus 12 to get 28 there, minus 28. Either way works. All right, next one. X squared plus 2x plus 1 equals x squared plus 5x plus 1. Again, it's not equal to 0. We want it equal to 0. So let's move everything over. If I move the x squared over, those are gone. Cool. So now I don't have to worry about factoring. The quadratic is gone. Move the 5x over. So 2x minus 5x, it's going to be negative 3x. Move the 1 over. Those are gone. So negative 3x equals 0. That's easy enough. X is just 0 if I divide out that negative 3. So if I plug 0 in for either one of these equations, that's essentially just going to ask me what the y-intercept is. In this case, it's 1. That's kind of nice. That was probably the scariest looking one that we did the fastest. Awesome. All right. Home stretch, people. We have 4 problems here that we'll kind of zip through. You know the drill. If you want to pause the video, maybe take a stab at these first and then double check to see if you got it right, or turn on the 1.5 speed and kind of rush through the explanation to see if you understand it. Go for it. Absolutely go for it. All right. So first one, we have x squared equals negative 4. Since this is already just an x squared all by itself, I can go straight to taking square roots. So x equals plus or minus 2i, and that tells me that there are no real solutions. That one was pretty fast. Cool. On to number 2. Negative x squared minus 3x minus 2 and x squared plus 3x plus 2. Well, it looks like these are just complete opposite functions of one another. So if I were to do elimination, I'd think I'd get a 2y equals 0. So I'm thinking some stuff might cancel out, or that I might get a y value of 0. But let's wait and see. So I've got x squared plus 3x plus 2 equals negative x squared minus 3x minus 2. We want everything over to the left-hand side so that it's equal to 0. That'd be 2x squared plus 6x plus 4 if I added all of these terms over to their corresponding terms to the left. I can pull out a GCF of 2. So I've got x squared plus 3x plus 2 in the parentheses. I'll continue to factor what's in the parentheses here. Numbers that multiply to be 2 but add up to 3, that's going to be 1 and 2. So my x values are going to be negative 2, comma something, and negative 1, comma something. So if I plug in negative 2 for x, I'm going to use the second equation because there's fewer negatives to deal with. Negative 2 squared is 4 minus 6 plus 2. 4 minus 6 plus 2. That's going to be 0. And I kind of anticipated a y value of 0 there too. Next one. We have negative 1, so plug that in. Negative 1 squared is 1. 3 times negative 1 is negative 3. So 1 minus 3 plus 2. And again, that would give us 0. We're rolling, folks. We are rolling. 2 more. Dos más. X squared minus 2x plus 1 and x minus 3, set them equal to each other. They're both equal to y, set them equal to each other. Again, we're going to find where do these things intersect if they do, but maybe they don't. It's not equal to 0. We want it equal to 0, so let's kick the x over to the other side. This would be x squared minus 3x. Add 3 to the other side, add 3, plus 4. X squared minus 3x plus 4. So we want to figure out when does this thing, or when do these lines intersect? So our goal, just like normal, is going to be to factor this out. So we need to figure out, okay, what values might factor out, what values might multiply to be positive 4 and add up to a negative 3. And some of us might be thinking, okay, well, that's easy. We got we got a 4 and 1, right? Because 4 minus 1 or 1 minus 4 is negative 3. But hopefully we're seeing an issue with that is if I did 4 and negative 1 or negative 1 and 4, well, that's not going to multiply to be a positive 4. So we've inherently made an error there. So factoring is not going to work. Factoring's out the window. That means this thing is not going to have a clean, pretty answer. So we could try maybe doing completing the square or quadratic formula. Well, if I did quadratic formula, that would be the opposite of b, so positive 3, plus or minus the square root of b squared, so it's 9, minus 4ac. Well, a is 1, c is 4, so 4 times 1 times 4 is 16, all over 2a. And looking at my discriminant here, 9 minus 16, that's going to give me a negative value, so we've got no real solutions. These things will never intersect. Last one. By the way, before we do the last one, if you ever hit a point where it's unfactorable, that means your answer is not going to be clean, pretty, rational numbers. If it's not factorable, your answer will be gross radicals or irrationals. Or maybe there's no real solution. So if it doesn't factor, that should be an alarm siren going off in your head that maybe there's no real solutions. All right, I digress. Last one. We'll set these equal to each other. X plus 5 equals negative x squared minus 3x plus 10. Again, if you had these flip-flopped as far as what side of the equal sign they're on, it doesn't matter. The whole idea of an equal sign is that the left side is the exact same as the right. We want this equal to 0, so we'll move the x squared over. We'll move the 3x over. So that'd be a 4x. Hey-oo. We'll move the 10 over, so we'd subtract that over. That'd be a negative 5. So now we've got a factor x squared plus 4x minus 5. Hopefully we don't run into that same debacle we just saw. So numbers that multiply to be 5 but add up to 4, I'm thinking 5 and 1. And then we just need to make sure that one's negative, one's positive. So if I did a positive 5 and a negative 1, that should work, which means I'd have x values at negative 5 and at positive 1. Now if we plug these in, I would argue that the equation x plus 5 is probably going to be the easier route. So if I plugged in negative 5 plus 5, I'd get 0. If I plugged in 1, 1 plus 5 would give me 6. So those would be the two intersection points that we have there. All right, folks. That sums it up. I'm going to zoom out on this last screen in case there's anything that you did not get to write down. But that sums up not only this lesson, but also this part of the unit. So, hey, we're all done. We did it. Yay. If at any point you guys have questions over any of this, please do not hesitate to reach out, send me an email, ask me in class, whatever. And as always, folks, good luck, have fun, be safe, roll tide.